A and B that you're finding the greatest common divisor of, and you find the greatest common divisor by the procedure that we did on Tuesday, in which we'll take some examples. We didn't have time to do examples on Tuesday. We'll do some examples now that I prepared. And then once you know the greatest common divisor is, say, 6, or whatever it is, you could find out what the linear combination is by solving the Diophantine equation, ax plus by equals 6. And so that will review Diophantine equations. So I'm trying to review things as we go along. So let me shut off the video and get into OneNote. And as I say, because you told me that you could see exactly the screen I had in OneNote as I was writing, one of the things, as I showed you, I see is instead of all the notes for the term, they're all there. I just didn't realize you didn't have access to them, so I have to get you access to them. But so let's go. So what I want to do is just say something about 2 to the power 1 million, and then take some examples from Tuesday where you actually compute the greatest common divisor, and then you'll do some homework on that. And then I want to prove one more theorem, which isn't that long, which says that no polynomial in n variables. So you know what polynomial in one variable is. Polynomial in more than one variable is just, you've had things like this when you've done partial derivatives. If you have something like 2x to the third times y to the fourth minus 6x plus 7y plus xy to the fifth, that would be a polynomial in the 2 variables x and y. So we will prove quite expeditiously that no polynomial in any number of variables can represent only prime numbers. There are some functions that have been developed that use the greatest integer function, the bracket function, that will generate only primes. There's no function that will generate all primes, and in fact, there's no polynomial that will generate even just only primes, not all of them, but nothing but primes. Even if you don't get all of them, you can't even do that. As I said earlier in the term when we were talking about prime numbers, there's no function that tells you what even one more prime is. If you're up to a certain prime, Euclid proved, we proved that the primes never end. There are always more primes, but to put your finger on exactly where the next prime is, there's no function that does that. So prime numbers are very mysterious, but because according to the fundamental theorem of arithmetic, they're really as I've said, the building blocks of all integers, which in turn are the building blocks of rational numbers and then real numbers and then complex numbers. Prime numbers are extraordinarily important. But because there's no apparent pattern among them, I've mentioned that one of the ways in which SETI, S-E-T-I, Search for Extraterrestrial Intelligence, one of the things they'd be looking for is perhaps, since presumably prime numbers in mathematics would be universal, radio signals that are in the form of prime numbers, or the periodic chart of the elements, so something that has no known natural cause. Anyway, let's go ahead. And so, as I say, I want to start by saying something about like 2 to the millionth power, and then take some examples from Tuesday's work so you see how it actually works, and then prove one more fairly small theorem, and then I hope get to some of the homework. I want to do the unique factorization homework, and we still have some on mathematical induction. So let's go ahead. Okay, here goes.
This meeting is being recorded.
Yeah, you see, I have all these previous classes that are in different bases, the infinitude of primes. I just assumed you could see that also. Okay, so for homework, find the greatest common divisor, the parentheses indicate greatest common divisor, of 40, 30, and 4704. And then the same thing, find the greatest common divisor of 525 and 168. And then once you have that greatest common divisor, find a linear combination of those numbers, 168 and 525, by solving the Diophantine equation, namely 168x plus 525y equals whatever that greatest common divisor is that you find by the method that we proved on Tuesday, and that we'll take some examples of momentarily. And finally, do the same thing, find the greatest common divisor between 385 and 182, and again, solve the resulting Diophantine equation, namely 385x plus 182y equals whatever you find to be the greatest common divisor. And so what you're looking for when you solve, of course, when you solve the Diophantine equation, in this case, 385x plus 182y equals the greatest common divisor, you're looking for the values of x and y. That's what it means to solve an equation, right? Okay, so, okay, draw. Okay. Yeah, so we saw that number k of digits in a number, I was using capital N, written in base, let me expand it, written in base B is k is the greatest integer in log any base of n over the log in the same base, whatever base you're using. And again, this is the bracket function plus 1. So we saw that written in base ten two to the 100th power has 31 digits. Again, base 10. Let's look at, I mentioned 2 to the millionth. And then I'll say something that you might find rather startling about this. So here, n is well, guess what? It's not working. Yeah, I'll stick it in again, but I've had it in for hours. And it did have a warning of 1%. So is evidently not taking the charge. All right, I have it in. I'll take it out. Oh, I don't know what that was about. Let's hope it continues and I don't have to keep interrupting to put it back in, because that should not, it's not working. Oh. Okay, so the number of digits is the greatest integer in the log base 10 of 2 to the millionth over, this is not good. Okay, the pen is not, the style, it's not working.
You can just leave it plugged in for like few minutes. You know, it'll have a quick charge, at least 5%. That should be enough for the rest of the lecture.
Well, all right, but I had it, I mean, I don't think it has to, wait a second, does it have to be turned on for the stylus to charge? I had it in for hours, but not with it, not with the tablet on.
No, the tablet does not have to be on. So if you can press this home button, and we can see what exactly is happening, if it's charging or not. So if you press the home button of the iPad, and since you're sharing your screen, I'll be able to see it.
So
They'll
what should I press the home? I mean, what will happen if I press home now? Am I going to be, well, I'll be able to get back into this, but I mean, should I get out of this first or just press home now?
Just press home, the home button of the iPad, because it will show if it's being charged. And then scroll to the left, you know, swipe left.
Swipe from the left?
Yes, from the left to the right. Yep. And then if you go up, you see that notification. If you scroll from, if you touch that, if you go up.
On the left side down to,
So you see where it says up next, the calendar, Siri app suggestion, and then you have Zoom, Firefox, OneNote.
Yeah.
So around there, just swipe up, you know?
So
with your
like,
hand. Yeah, but the other way, keep going. I think it should be, keep going. Keep going. Because usually there'll be a menu, or just go up, go the other direction then, please.
When you say the other direction, you mean downward or?
Yeah, downward. Yeah, all the way to the top.
Okay.
Keep going until you can no longer go.
Okay.
Well, let me check my iPad. Yeah, because if it's charging, there'll be a little notification saying that it's charging.
The battery on what? On the tablet or on the?
Professor, you can also go to the setting to see. Scroll down. That's
Zoom.
Go to Bluetooth.
There's supposed to be a Apple Pencil because on my iPad there is an Apple Pencil, and I can check the battery.
Is the pencil on the left or on the
No,
right?
It's supposed to be on the left side.
No, Zoom, Word, OneNote, other thing, Firefox, Dropbox, music, Safari. Battery, but the battery is for the battery on the tablet, not the pencil.
Yeah, it should. The Apple Pencil should be underneath. Yeah, click on Bluetooth just in case to see what's going on. It's connected. Can you click on that information?
Forget
Just let it charge for
this
2-3
device.
minutes. It charges very quickly. We know that it's connected. For whatever reason, maybe it wasn't connected properly prior to this lecture, and therefore it wasn't getting charged. Sometimes it seems like it's plugged in, but it's not. That can happen as well. So just leave it for like 2-3 minutes. It really charges very quickly. It has a supercharge, and it will give you enough, like 5%, and 5% should be enough for the rest of the lecture.
Yeah, I mean, that's what Professor Ronan had told me, that it really needs only, for a particular class, it needs only, like, yeah, as you say, a few minutes. All right, well, okay, so you think it's charging?
Since it's connected, I would, and make sure, like, make sure the pencil is snugly plugged into the iPad.
Yeah, kind of clicked in. I mean, the way I've always been doing it. Well, anyway, okay, so while we're waiting for this, we've done this before, so let's continue. So what we had there was the number of digits base 10 in 2 to the 2 to the millionth power is the bracket function, the greatest integer function. It's a fraction. The numerator is the log base 10 of 2 to the millionth power over the log of the base that I want to change it to, which is base 10. And I'm choosing 10 as the base for the logarithms. And as one of you said on Tuesday, I guess it was, unless it was last Thursday, that the log of the base itself, that is the log of 10, base 10 is 1, because as I reminded you, a logarithm is an exponent placed on the base. So if the base is 10, the exponent that you put on 10 to get to 10 is 1. So the denominator becomes 1. And then using the fact about logarithms, that the logarithm of a number to a power is that power times the log of the number. And then outside you have the plus 1. And so that equals the greatest integer in 1 million times the log of 2, and then that's over 1. The greatest integer in that, then plus 1. Okay, so I looked on the calculator to get more decimal places for the log base 10 of 2, and I got the 3010 we already had, and we're going to have to multiply it by 1 million, right? 1 million times log of 2. So we're going to have to move the decimal point over 6 places. So let's take 7 places just to see what's happening. And so what I got there for 1 million times the log of 2 is 3. So multiplying the log of 2. Well, what I got for the log of 2 was 0.3010, like what we had, then 2999, then 57. So if you put in, so to multiply by a 1 followed by 6 zeros, which is 10 to the 0th, you move the decimal point 6 places to the right. So let's write the log of 2 as 0.30299. And then 1 million times that, so this is still in the brackets, 1 million times the log of 2 would come out to be 301029.9, but you're taking the greatest integer in that, so you're going to drop that 0.9 afterwards and just be left with the whole part of the integral part. And so that comes out to be, when you take the bracket function, it turns out to be the number 301029, and then you add 1 to that, and because there's that plus 1 outside the brackets, you get 301,000. That's 301,030. So 301,030 digits. Now, let's look at that number. So 2 to the millionth. Again, look at the power of power. Look at 2 times 2 times 2 times 2, exponential growth. To write 2 to the 100th power, we found you need 31 digits. To get 2 to the millionth power, you need over 300,000 digits. You need between 250,000 and 1/3 digits. Now, if you were to write that number with 301,030 digits at the rate of 1 number per second, without stopping, you're just writing the number, those 301,030 digits, at the rate of 1 a second, and not stopping to sleep, not stopping to eat, not even stopping to look away for 1 second. I computed that it would take 3 days, 11 hours, and 37 minutes to write the digits of that number. Now, let me emphasize, it would take that long just to write the digits of the number. I'm not talking about counting up to the number. I'm just talking about writing the number. So, for example, it would take, at the rate of 1 digit per second, it would take 4 seconds to write the number 1,000, 1, 0, 0, 0. But to count up to that, to count up to 1,000 at the rate of 1 number per second, I computed it would take 16 minutes and 40 seconds to count up to 1,000. So look at the difference between the number 1,000. Writing the digits of the number would take a mere 4 seconds, 1, 0, 0, 0, but counting up 1, 2, 3, 4, up to 1,000 would, at the rate of 1 per second, would take 16 minutes and 40 seconds.
Professor, excuse me.
Yeah.
I can only see like the Bluetooth screen. I can't see your OneNote.
No, I can go back to OneNote? Oh, okay. I left it there. Okay,
Unplugging the pencil now and see how it should. I mean, it should have enough battery for now. If the pencil is working, you should be fine by now. You should have at least 3 to 5% of charge.
Oh yeah, all right, here goes. Well, let's hope. Otherwise, we're sort of in trouble. Okay, so I guess I have to, go back. Oh, all right. I'm afraid to try it because, well, okay, that doesn't prove anything. Okay, so over log 10 base 10 plus 1, and so that equals 1. So this equals greatest integer in 1,000,000 times log base 10 of 2, close brackets, plus 1. And so this is greatest integer in 1,000,000 times, Where is that? 0.301029.9. Okay, so multiplying by 1,000,000, moving a decimal point over 6 places, we get 301,029.9 plus 1. And so the greatest integer in that, that's the biggest whole number part, it's this, equals 301,029, and then we have the plus 1. And so that equals 301,030 digits. That's to write not count up to, just to write. So for 2 to the 100th, we got 31 digits. And again, there's a difference between writing the number and counting to the number. So for instance, 1,000 has 4 digits, but it takes 1,000 numbers to count up to 1,000. Now, just to gain some idea of the magnitude of these numbers, what does this even mean? 31 digits, or over 300,000 digits? Okay, so we usually think of a year as being 365 and a quarter days. It's actually slightly less than that. Instead of 365.25, which would be a quarter, it's a little less. It's 365.2422 days. So eventually, a leap year adjustment will have to be made. So a leap year is a year divisible by 4. Except if it's if it's divisible by 100. So there have to be slight adjustments over long periods of time. And an estimated 13.7 billion years since the universe presumably started in the Big Bang. Okay, so in 1 minute, there are 60 seconds. In 1 hour, there are 60 minutes. So that's 3,600 seconds in an hour times 24 is the number of seconds in a day times the number of days in a year. There's 365 and so on, times the number of years, 13.7 billion. I found that there have been 432 quadrillion, 329 trillion, 880 billion, and then I just use that many significant digits. So after that, million, thousands, units. So units, thousands, millions, billions, trillions, quadrillions. Yes, that many seconds. And if you take a look at that, so just look at the size of these numbers. 2 to the 100th power written in base 10 has 31 digits. 2 to the millionth power has, more than 432 quadrillion digits. In the whole history of the universe, you can express the number of seconds since the presumed Big Bang, presumably 13.7 billion years ago. The total number of seconds, to count them, you need only 18 digits. So an innocuous looking number like 2 to the 100th, it doesn't look so formidable. It has 31 digits. The number of seconds in the whole history of the universe, not the Earth, not the sun, not the solar system, not the galaxy, the whole universe requires only 18 digits. Wow. And yet, compared to infinity, 2 to the millionth power is no closer to infinity than 1 is. So think about that. All right. So let's take some examples in finding greatest common divisors. Well, I guess you're right. The stylus is working now. After just a few minutes, maybe I didn't have it put in properly before, or you said it does charge even when the tablet is off, I would imagine, but it seems to be working fine now. Wow. Okay. So I think you might find it easier if we introduce a little terminology. Suppose we have 4 into let's say 27. All right, so 4 into 27 is 6. then we multiply back. That's the BQ in the division algorithm. You multiply it back, and then what do? So A is 27, and it equals B, that's 4, times the quotient is 6, plus the remainder. So if you subtract that, you get the remainder. The 4 is called the divisor. The 3 is the remainder, which could be 0, but in any case is less than the divisor. The 6 is called the quotient. And I don't know if I've used this word. I haven't heard it much since about the 4th grade. Anyone know what you call the number that you're dividing into?
Dividend?
Yeah, very good. That's a dividend, right? So, yeah, very good. So if you have, for instance, A equals BQ or QB, I think I wrote it as QB on Tuesday, plus R. So yes, so the A is what you're dividing into. Yes, that's the dividend. The Q is the quotient. The B is the divisor. And the R is the remainder. So I think you might find it easier to remember what we proved if I write it in words. What we did was start by writing the statement of the division algorithm. Start by writing the division algorithm, dividing the small number into the bigger number. And then what we did was in each successive step, one after the other. So we're going to repeatedly use the division algorithm. How? With the divisor moving over to become the new dividend. And the remainder moving over to become the new divisor. Wow, this is working great. Thank you so much for the suggestion. So what I'm saying is this. If we start with A equals QB plus, say, R, the next step, the next division algorithm, the divisor, we're dividing by B. So here, up here, the divisor, right? What I wrote at the top, A equals QB plus R. So the B is the divisor. So the divisor is going to move over to become the new dividend, and the remainder is going to move over to become the new divisor. So the next step here, and then we'll do a few numerical examples, but I just want to show you in general what we're doing. So we start by writing the division algorithm for A and B, divide the smaller of the two numbers into the bigger one. And then for the next step, instead of A being the dividend, we're going to make the previous divisor B into the new dividend, what you're dividing into. Again, look up where I wrote A equals QB plus R. So what you have on the left there is the dividend. So the old divisor B, I'm talking about up here, the old divisor B moves over and becomes the new dividend. B equals some Q sub 1. I don't want to use the same Q because, and the previous remainder moves over and becomes the new divisor, and then we have some other remainder, R sub 1. And then you keep doing this, repeat until the remainder, let me go to the next line. And the last non-zero remainder, what I called in the proof on Tuesday, R sub K, is the greatest common divisor. So so this is what we had on Tuesday, and I asked you, we did it, but I asked you to take a look at it. So notice on the first line, we have A equals some Q sub 1B plus R sub 1, and then notice in the second line, the B, which had been the divisor, moves over and it becomes a dividend, what you're dividing into, and the new divisor is the previous remainder, R sub 1. So the remainder moves over in the second line and becomes the divisor plus some new remainder. In the line after that, again, the previous divisor, which was R sub 1, moves over in the third line now. The R sub 1, which had been the divisor in the second line, becomes a new dividend. There it is, R sub 1 equals some Q sub 3, I guess we're up to. And the remainder, R sub 2 in the second line, moves over and becomes the divisor in the third line, plus some other remainder. And what we talked about, I asked you to actually, go through this and verify as you move up. And so you keep doing this until the remainder becomes 0. And then that last remainder, the R sub K, is actually the greatest common divisor of A and B. And remember what the greatest common divisor of two numbers is. It's the it's a common divisor, obviously. If it's the greatest common divisor, it's a common divisor, but also any common divisor of A and B divides it, and that makes it the biggest common divisor. And so if you work upwards, if you look at the arrow on the left, you see that you keep dividing by the remainder, and the R sub k turns out, as you move up to the top, to divide A and B, so it's a common divisor. And then on the left, I have an arrow going down, where if you start with any common divisor of A and B and trace it down, you'll see that that common divisor, called D, divides R sub k. So this R sub k, which I underlined on Tuesday, there it is at the bottom, that's the last non-zero remainder that we saw was the greatest common divisor of A and B. So let's come back to today's work and take some examples. So I just sort of here, I wrote examples, but I started by just writing a sort of summary of the instructions. Let's find, let's say, the greatest common divisor of 27 and 15. Okay, so we're going to start by writing the division algorithm, where we're dividing the bigger number, that's 27, by 15. So it's going to be something times 15, so that's like the B, plus a remainder. All right, 27 equals how many times 15? Well, not 2 times 15, that would be 30 already. So we'll have to write 1 times 15 plus a remainder of 12. Okay, so second line, the divisor moves over and becomes the dividend. So we have 15 equals, and then the remainder moves over and becomes a divisor. So it's going to be some quotient times 12 plus, well, we'll see what the remainder is. Well, okay, so we have 15 equals what times 12? Well, 1 times 12, and then there's a remainder of 3. Okay, so the remainder isn't 0, so we continue doing this. The previous divisor becomes the new dividend, so that's 12 equals some quotient times, and then the new divisor is the previous remainder, so going to divide by 3. Oh, 12 equals 4 times 3 plus 0. So the last non-zero remainder is the greatest common divisor. All right, I mean, that doesn't surprise you. I mean, the numbers are small enough, you probably could have seen that readily enough. But, you know, for bigger numbers, you can't just look at it. Let's do another. Let's find the greatest common divisor of 148 and 92. All right, so we're going to start by dividing the bigger number by the smaller number, using, you know, write the statement of the division algorithm for that. So we have 148 equals something times 92 plus a remainder. 148, 2 times 92 would be, be close to 200. Okay, so this has to be 1. So it's 1 times 92 plus, okay, to get up to 148 from 100 is 48 plus 8 more. So that's plus 56. All right, second line, the previous divisor moves over and becomes the new dividend, and the previous remainder moves over and becomes the new divisor. And 92 is how many times 56? Well, that'll be 1 times 56. So that takes you only up to 56. So to get up to 92, we need 66, 76, 86, 90, 36. Okay, next line, the previous divisor moves over and becomes the new dividend, and the previous remainder becomes the new divisor. So something times 36, 72. Okay, so we can see this is going to be 1 again, plus 36, 46, 20. All right, so we still don't have remainder of 0, so we keep on doing it. So the previous divisor moves over and becomes the new dividend. So we have 36 equals, and then the previous remainder moves over and becomes the new divisor, 20, times 1, obviously. So 36 equals 1 times 20, with a remainder less than 20 of 16. All right, we still don't have a 0 remainder, so we repeat it. The previous divisor becomes the new dividend. 20 equals something times the new divisor is going to be 16. And we can see that'll be 1 plus 4. Well, the divisor still isn't, the remainder still isn't 0, so we repeat. The previous divisor becomes the new dividend. 16 equals something times, and the new divisor is the previous remainder that moves over and becomes a divisor, and we get, so that'll be 4 plus 0, and so last non-zero remainder is the GCD. So if you wanted to find a linear combination, that gives that greatest common divisor, it would be well, okay, it would be 148x plus, I'll tell you why I hesitated, plus 92y. And we are supposed to be able to, according to the theorem we proved earlier in the term, we should be able to express the greatest common divisor, which is 4, as a linear combination of 148 and 92. So it would look like that. Now, you could do it that way. And so that's a Diophantine equation. But it would be easier if you remember how to solve a Diophantine equation. If not, I'll just remind you of it. It would be easier to, I don't know, easier. It wouldn't be easier. It would be notationally, it would be easier to write it as, put the 92 first. Instead of the greatest common divisor of 148 and 92, the greatest common divisor of 148 and 92 is the same as the greatest common divisor of 92 and 148. So suppose we put the 92 first plus 148y equals 4. So again, that's a linear combination of, it doesn't matter whether you say 92 and 148 or 148 and 92, it's the same two numbers, right? The reason for that was, if you remember how to solve a Diophantine equation, we expressed we used the famous division algorithm to write the other two numbers in the form of dividing by 92. And since you're going to divide by the first number, it's convenient to have the first number, the smaller one. So when we're finding the greatest common divisor, we started here with 148. We started with the 148 first and then the 92 because you're dividing the bigger number by a smaller number. Well, you're doing the same thing in the Diophantine equation here, but this time, since the way we did it was dividing by the first coefficient, it was convenient to make the first coefficient the small one. You don't have to. We once did an example where you didn't do it that way, but this would be easier. So then you get all terms. So we're dividing by 92. So we'll have three terms with 92, put the other two terms on the other side of the equation, and then those two terms are divided by 92. So what does it mean to say those two terms are divisible by 92? It means those two terms equal 92 times some z, and that gives you a second Diophantine equation, and you keep doing that until you finally, until the new first coefficient eventually actually divides the constant on the right. Remember, though, remember, we derived the solution of the Diophantine equation predicated on the fact that the coefficients, in this case 148 and 92, or ax plus by equals, I guess I used n, the coefficients, the a and the b, the ax plus by equals n, have to be relatively prime. So solving the Diophantine equation requires that the coefficients be relatively prime. How do you do that? So for instance, over here, so for instance, in what we have there, 92x plus 148y equals 4. first divide through by the GCD, which we found up here was 4. So the actual reduced or simplified, whatever you want to call it, Diophantine equation is, see, if we divide by 4, that's going to be 2, 3, is that right? 4 into 92 is 2, 3x plus 3, 7, is it? Uh, 4 into 14, 74, yeah, 37. Let's do one more. Let's find greatest common divisor between 75 and 14. All right, so again, how do we do it? I summarized it back here. Where it says procedure. So we start by writing